Markov string. And so it was important for us to have eta mu z. So I guess what you're saying is that a coherent state of graviton does not necessarily imply that the space-time is always curved. Yeah, I agree with that. Yeah. So, and we will see more precisely. I guess. Yeah, but it's kind of an obvious. Yeah, it's an obvious thing that. All right, guys. So we'll see some of the things in a second. Okay. So we have a nonlinear sigma model, right? And so in that nonlinear sigma model, the Wolfsheet fields X become coordinates in the target space. So let me write this down explicitly. X mu are coordinates on a target space of this nonlinear sigma model, which is two-dimensional quantum field theory. And those guys, G mu, D mu, and then phi, are fields in target space. So in order for me to show that they are fields, they must satisfy some equations of motion, right? For now, those guys are just condensates, right? They are condensates of coherent configuration of graviton, a coherent configuration of massless open string state. So the first observation is that in general, as sigma is an interacting quantum field theory, interactive QFT in 2 dimensions, right? So there are lots of interactions, and the way to think about it. So what I can do, I can go back to G mu. So then I have del x mu, del x mu. So those are the Wolfsheet indices. And so what I can do, I can expand this about some classical configurations. So I'm going to say that x is going to be equal to x naught. So some fixed classical configuration, classical, plus fluctuations y mu as a function of sigma. So those guys are independent of sigma, and y mu are fluctuations that depends on the coordinate in the Wolfsheet. You can think of this as when my string propagates. The way how the string propagates describes by embedding, right? And so x mu provides the embedding of a Wolfsheet into a target space. And so those guys are sigma independent. So you can think of this that describes the embedding of a center of mass string, right? So it's a center of mass. It's independent on sigma and describes how the center of mass propagates. But now, once I do this expansion, so what's going on is that there is G mu as a function of a center of mass coordinate. And then there is an infinite series of derivative expansion, right? So I'm going to expand this as a Taylor series expansion here. So this is going to be G mu derivative with respect to rho, by rho plus lots of other terms. And then I still have del A y mu, del B y mu. And so what you see here is that now this term describes a cubic interaction on the Wolfsheet. So indeed, this nonlinear sigma model describes a non-trivial interacting quantum field theory. So it turns out that as a two-dimensional quantum field theory, this QFT, so as sigma is a renormalizable quantum field theory, and I'm not going to go into discussion why this is renormalizable, because I know some of you are still taking the second course in quantum field theory. But take it for granted, it's a renormalizable quantum field theory, even though it contains an infinite number of interactions, right? So here I just truncate into the first term and produce cubic interactions, but I can go ahead and do further expansions, and so there will be an infinite number of interactions. Nonetheless, it's renormalizable, and so there is a parameter, right? So there is kind of a weak coupling limit in this nonlinear sigma model. And the weak coupling limit is determined, so there is a geometry in a target space. How strongly curved is my target space? So the expansion parameter in this interactive quantum field theory is alpha to the 1/2 over R sub c. So where R sub c is a radius of curvature of target space. So this guy is just L string divided by RC, and so this shows up if you study in detail when it's in which stance this sigma model becomes weakly coupled. Then that corresponds to a limit when this guy is much less than 1. Intuitively, it's clear what this means, right? So, in order for me to get a simple quantum field series, one that I can solve, it must be quadratic, right? So the fields must, the effective action must be quadratic, much like in a Polyakov string. And so that will be the case. That will be the case when only this term matters, right? Because when this term matters, this guy does not depend on sigma, and so I have only quadratic kinetic terms. And now you ask yourself, so what does it mean? So in some sense, what this means that what matters is that our string dynamics of the string is determined by the dynamics of the center of mass of the string. So you ask yourself, when this is the case, when a propagating string in external curved space-time can be replaced by a propagation of its center of mass. And that's the case when the string is very small, right? So the string is very small compared to a characteristic length scale in the target space. Then that's a very good approximation, right? So in other words, that's exactly when I can make these derivative expansions, use the Taylor series expansions about classical configurations involving motion of the center of mass. And that is precisely the condition, right? So if my space is curved, so the size of my string must be much, much less than the curvature scale, right? The curvature radius in the space-time. Is this clear? Okay, so very good. So this is a quantum field theory with interactions, and so what we do for 3+1 dimensional quantum field series, we can study this as a quantum field theory. We can compute loop corrections, and so in particular, we can generalize something that we discussed before, and so we can ask the question when this nonlinear sigma model is invariant under wild transformations. So what are the conditions that, so while invariance implies that stress energy, the Wolfsheim stress energy tensor is traceless, and so we can ask what, in this interacting quantum field theory, what is the condition that the stress energy tensor is traceless? Okay. So that involves computing loop corrections, something that we haven't done. Okay, so this is, remember that when we guessed what the stress energy tensor anomaly was, right? So we did this in by asking what are the possible terms that can show up here. We can do this as a nonlinear sigma model as well. So this is an interactive QFT. And so I'm going to write this down as -1/2 alpha prime. And here I have beta mu. I put a subscript G. So these betas, they depend on, well, okay. So let me write it down first. And then I have GAB, del A x mu, del B x mu, plus, I'm going to use a conventional normalization, minus I over 2 alpha prime. And then I have beta E. Then here I have mu of epsilon AB del A x mu. Okay, and then there is a last term minus 1/2 beta phi, which is there. Okay, so remember that the structure here, TEA, is del x squared plus r, which is exactly the same structure when we asked the question, if while invariance is violated by quantum corrections, what are the possible Walsh-Heath operators that can come up here? And the only two operators that we come up with was del x squared and r. And so what we said that, well, in the case of a flat string, we have a flat, sorry, in the case of a string propagating in Minkowski spacetime, and when the Walsh-Heath is flat, then we argue that this guy is 0, and the coefficient here was related to the critical dimension. That's what we did before. So, so this argument, what operators can come out in the computation of quantum field theory, I can repeat literally. And the only thing that happens here is that there is a different tensor structure, right? So this term is also del x squared, but this is symmetric in AB. And this guy is anti-symmetric. And so, so here there were arbitrary constants here. That's because we looked at a specific Polyakov string, right? So we looked at a Polyakov string in flat space-time, no condensate of dilatar, no condensate of this B field. But in general, there will be some functionals here, right? So these are these beta G, beta B, and beta phi that will depend on the fields, right? So they will depend, they will be functionals of the metric, the two-fold field, and the dilaton. And it requires a work. So you have to do a loop computation. It's not only a sigma model to actually compute what's there. Okay. We haven't done it in the case of a Polyakov string, and I'm not going to do it here. Even Joe doesn't do it in his book, but it can be done, and you can look at the papers where this is done. So there is a reference, and for example, Hadi Zeitlin did a lot of work on here. But the bottom line is that you can compute exactly what those guys are. So I'm going to write it down. So beta mu G equals, okay? So first of all, this is a two-dimensional quantum field theory, and the effective coupling in this two-dimensional quantum field theory is alpha prime, right? And so what you have, much like when you compute beta functions in gauge series, you have a perturbative gauge coupling expansion there. So here you have alpha prime expansion for the Walsh-Heath beta functions. And so what you have is alpha prime. So here you have R mu plus 2 nabla mu phi minus H mu lambda O H mu lambda O plus higher order corrections, right? So I'm writing down terms which are linear in alpha prime, okay? So this H, right, is a field strength of the B field. And so this guy, R, is not the curvature on the Walsh-Heath, but it's a curvature in space-time, right? So this is a Hardy. Okay. So that's the first equation. So this is a beta function that couples to del x squared. And you can see immediately why we didn't have this term when we looked at the Polyakov string. Well, for the Polyakov string, this guy is 0. Okay? This guy, we don't have a dilaton, so covariant derivatives of 0 is 0, and we didn't have any B field, so this guy is 0. That's why this guy was not in our discussion. So similarly, for beta mu of B, right, so this is the beta function that couples to an antisymmetric combination of del x's. So it takes this form alpha prime minus 1/2 nabla rho h rho mu plus nabla rho phi. And here I have h rho mu, and then here I have put out squared. Okay, so that's 2. And then there is the last one. Right? Minus 6 plus alpha prime minus 1/2. Good. So, and in fact, you can see now for this beta function for the dilaton, again, this is a piece that we discussed before. So this term is the one that multiplies by the Wiltshire-Ricci scalar. And so we looked at the Polyakov string, and so this term actually wasn't there at all. And so the only contribution was d minus 26 divided by 6. And so the conditions that the stress energy tensor, Wiltshire stress energy tensor is traceless, gave us the critical dimension. And all I'm saying here is that when you do this one loop computation in this interactive two-dimensional QFT, then you will get these expressions for the beta function. Right? And so finally, so that tells you that the conditions that we have wild invariants are the conditions that the beta functions vanish. And those are the condition in the language of quantum field theory. Those are the conditions that were telling us what are the consistent values of Fokker condensate, right? So that's what was speaking for us, the vacuum of quantum field theory, right? That were minimal of the potential. So now in the string series, those conditions are replaced by conditions that beta functions corresponding to wild transformation on Wiltshire vanish. Okay, and so that produced some very surprising equations. Okay, so if you stay on long enough, and of course there are corrections, and I believe it has been computed maybe to fourth order. So we have higher order corrections here as well. And in principle, again, much like in any quantum field theory for which there is a perturbative expansion, it's just a matter of technical capability, how many loop diagrams you can compute. So we have this condition, and then the question that people ask is, so this looks awfully like, for example, if I look, kind of going along the questions that you asked, that being flat does not necessarily mean that it's Minkowski, right? So the simplest question you can ask, so let's suppose that we look at the stream propagating when there is a constant dilaton, so phi equals 0, and then I have B field mu equals to 0. So what is the condition to leading order, right? That I described a consistent propagation of the string. So you can see that the only thing that is non-trivial will remain this beta function equals to 0, and that corresponds to R equals to 0. So what this tells you that your string can consistently propagate in spacetimes which are flat. Okay, but that doesn't necessarily imply if the spacetime is Minkowski. So the string can propagate in wherever solves this equation. And that's the first time what you have here are the Einstein equation. E equals 26, right? So we need to put D equal 26 because we have to require vanishing of all the beta functions, and vanishing of this beta function to leading order tells us that D must be equal to 26. In some sense, what I'm doing, I'm talking about perturbative expansion of this in terms of alpha prime. But it's also clear. Okay, so this is just one example. You can construct other consistent backgrounds in which the string can propagate. But what you can ask a more general question. More general question is, so there are this equation of motion that consistent backgrounds must satisfy. But can I write down the Lagrangian for this consistent backgrounds? So in other words, we're asking the question, what is the effective theory for consistent backgrounds of closed string propagation. Okay, so in some sense, this is analogous to a question when we do this expansion, right? So this, I was telling you that that's a motion. That describes the motion of a string in center of mass of the string in external spacetime. And so, so the equations that we wrote up there are the equations which tell you what are the consistent spacetimes in which the center of mass of the string can propagate. Okay, and once you have this equation, you kind of go back and you ask yourself, so what's the effective action? What's the Lagrangian that describes that? And since we're doing it perturbatively in 26 dimensions, right? So I have to satisfy these equations perturbatively. So as the first to leading order, I have to put. Well, okay, sorry. I can write down this in general. So the target space, the effective action is a target space. Takes the following form. So this is 1 over 2 k squared. So k squared is a constant, so that's a gravitational constant. And then I have, I'm living in d dimensions now. So this is minus g square root of minus g. So this is a target space metric, e to the minus 2 phi. And then I have minus 2 over 3 alpha prime and d minus 26 plus r minus 112 h squared plus 4 alpha phi squared, and then plus 4 alpha prime squared. Okay? So it turns out that if you have this effective action, and in this effective action, you just vary. You take this as your effective action for the fields, metric, G. So this is a target space effective action for G, and phi. And so if you just derive the equation of motion coming from this effective action, you will get exactly the condition for vanishing of the worldsheet beta function. Okay? So what I did here, I just organized this effective action in the alpha prime expansion, and I wrote the beta function just to this quadratic order in alpha prime, and so there are two terms here as well. Okay, and so now in particular, it's especially clear when this approximation is valid, right? So when the approximation, the derivative approximation we'll be making here is consistent, and that is the case when the higher derivative correction will be subdominant. So in other words, our target space curvature is very small. Let's see, what do I want to say here? So you might, okay, so let's talk a little bit about this. So if you really want to trust the computations that you make with this effective action, the first thing you have to do is you have to set d equals 26. Okay? Because if you don't set d is not equal 26, you can still solve the equation of motion that comes from this action, but you will no longer be able to argue that these higher order corrections will be subdominant. Right? Is this clear or not? No. Why is this so? Okay, so if d is not equal to 26, this guy is not 0. Is it clear? And then I have the terms which don't involve any alpha prime. What this means? This means that, for example, the curvature must be such that it cancels one of the alpha prime terms. So the curvature is for the alpha prime. So you are in a regime when r sub c, the radius of curvature is alpha prime. So you are in a regime when this guy is 1. And I was telling you that you need this expansion parameter in order to write down this alpha prime expansion of the beta function. So you are violating the condition that you have consistent expansion in alpha prime whenever you look like for solutions when d is not equal to 26. Is this clear now? It's just really thinking. So I have perturbative expansion of this effective action, and I want to make sure that whatever terms come up here, they will be subdominant compared to what I have here. And the thing is that because this guy has units of length, so all the terms here will involve higher derivatives higher than 2. So for example, in the string theory, there is a term which is alpha prime 2. And so this term involves up to the 4th term. So if you take a Riemann tensor and you contract it in various ways, there is a very specific way how you have to contract it. But this is a high derivative correction. Okay? And so this is a term that will show up somewhere in higher order expansions in this alpha prime. And so what I just told you, you have to be really amazed. Because not only does the string theory reproduces the Einstein gravity, right, to leading order, but it also predicts an infinite set of corrections, right? So in principle, in order for me to compute what are the corrections to the Einstein equations, all I have to do is just take that worldsheet action and just compute the beta functions, to higher loop order, and then go back and say what is the effective action for the metric and B, the dilaton, that will reproduce that equation. Okay. So in this sense, the string theory not only reproduces the Einstein gravity, but it also tells you where will a deviation occur, and the deviation occur with a characteristic scale, which is this alpha prime. So any questions, guys? Yes.
Good question. So this expansion is not valid for R equals 0.
Yes. What this means is that you have very highly curved space. A flat space has R sub c equals infinity. So it's a radius of curvature. So when curvature is 0, the radius of curvature is 1 over square root of for each scale.
Like if other dimensions are correct.
Right, so we can talk about this a little bit. So, I'll say about this in a second. But Let me do one more step. So you have this, and you say, look, you are lying. Right? This is not Einstein gravity. I mean, there is what you did here. You wrote Einstein-Hilbert term, and then there is e to the 2 so this is something like Brent-Sticky gravity or something like that. But I'm not lying to you. The reason why this is Einstein gravity, and that's why honestly I could never understand why there is so much well, by the way, so in this language, what you see, you kind of see, if you define the coefficient in front of Einstein-Hilbert term, okay, so if I define the coefficient in front of which is scalar square root of minus g, then it depends on x, right? So because my kiloton can depend on x, can depend on time. So I have a dynamical evolution of my Newton constant, okay? And that's what people like to talk. But what I'm going to show you is that I don't think that there is any content here, or we shouldn't be making a strong statement. But I'm saying that that's sometimes when you start going into that direction, you can mislead yourself. And the reason is because there is a trivial frame or trivial field redefinition in which I don't have any of them. I just have a standard description in which I have a fixed Newton constant. This guy, by the way, is gravitational constant, is 1/16 pi g Newton. Okay? If we were in 4 dimensions, then 1/16 pi g Newton is something that I would put in front of that. So in the model that is written there, in this effective action, the Newton constant can change in space and in time. But I'm saying that that's a misleading thing. And the way to show you that that's a misleading, I'm just going to make the following statement. So I have G mu nu, and what I can do a field redefinition. I can simply redefine what I mean by my metric. And so if I'm going to do it in this way, so I go from G mu nu to G mu nu, and I put superscript E, meaning that Einstein frame, right? So this is Einstein frame metric. And so if I define it as e to the minus 4 phi divided by d minus 2, and then g mu nu. And so this g mu nu is a sigma model or string metric, right? So this is a sigma model or string frame metric. Right, so this guy is actually natural when we write down the nonlinear sigma model. And so on the worksheet, what we have this, and this guy, a string frame metric. So if I do this redefinition, how does my action would look like? So now I would have what I call an Einstein frame action. By the way, this guy has another kind of funny property. Not only it looks like that there is a space-time dependent Newton constant, but there is another feature. The scalar field, which is a kiloton, has a long kinetic term. And so then there is a lot of bad literature about, kind of consistency or inconsistency of propagation of ghosts in theories which are not Einstein. But again, I'm saying that all this thing will go away if you go to Einstein frame metric. Because once I do this change of variables, what will happen? And so I'm going to leave from now on in b equals 26. Because only in that case, I can trust this effective action. I argued you that if for some reason you found the solution such that you must balance this term with respect to this, then for those backgrounds, you cannot neglect higher order corrections. Okay? So any consistent backgrounds that you must write down must be such that you don't balance those terms. So this term must vanish by itself, which implies that G must be equal to 26. So then 1 over 16 pi G Newton an integral over d26x, right? So now we are living in 26 dimensions, minus G Einstein frame. And so here I have Einstein frame, which is scalar, and then I have minus 1 over 12 e to the minus 8pi over okay, d minus 2 is 24, so 5 over 3 h mu o, and then I have minus 6. Okay, so this one, and then there is of course possible higher order directions. Okay. So here you see a standard Einstein-Hilbert term. The Newton constant is fixed. It's well defined and it doesn't change. So this is a generalization. If you would have a Maxwell term, then it would show up as f mu minus a quarter, right? But so this is a generalization of a Maxwell field in which you have an asymmetric and 3 field strands. And then there is a dilaton. And notice that what happens that after I make this rescaling of the metric, not only did I get the standard Einstein-Hilbert term, but I also get the correct minus sign for the kinetic term of the dilaton. Okay, so this is a low energy effective action for the closed string, right? In the Einstein frame. This is low energy effective action. Focus on, okay, guys. Not only am I running out of space, I'm running out of chalk. Bosonic string. Okay? Good. So, right. So what will happen? Yes.
Is there a physical interpretation of why there's this interaction between the phi and each? So there's no interaction with
No, well, okay, interaction with the Ricci scalar.
Yeah.
So that's a trivial, kind of a trivial statement. Right. So there is. Unfortunately, it will force me to go into discussion of something that I can mention something. So suppose you do quantum field theory, right? Once you have an action for the quantum field theory, you can study perturbative quantum correction, but you can study also solitons. So what are the solitons? So the solitons are semi-classical, I would say, well, very often what you do, you just solve for classical equation of motion in your quantum field theory and you study solitons. For example, if I have a scalar field with multiple webs, I can study solitonic configurations that interpolate between one web and the other. Right? You can just find the equation of motion for phi that go start at one well and then at the other. Exactly the same thing here, right? So think what you did. So you started propagation of a string, okay, and now you make an approximation that you look at the propagation of a string in the backgrounds, which are not very strongly curved, and then you approximate the string by its center of mass. If you wish, all the string excitations are hidden in these higher derivative corrections. So in some sense, you look at the spacetimes which are very, very gently curved, and then your string looks like a point particle. So that's a point particle limit, if you wish, of a string. And so then you have a very specific equations for the background. And then you ask, are there any solitons here, right? Kind of the same way how you would be asking in any ordinary quantum field theory. And the solitons are usually non-perturbative effects. And so in this way, you will find exactly in this action, you will find a soliton that will carry a charge. Sometimes you can think of this as it will carry the dilaton charge. It will carry the charge. It will carry this H field charge, and it will couple to a dilaton. So I guess, okay, so what I'm trying to say is that there are solitonic solutions in this point particle approximation to string theory, which are charged, and those walls, they behave as a source charge for the dilaton. That's why there is that coupling. Okay, so notice that those solitons, they must carry this charge under this field, because if this field is zero, then there is no coupling. So some of you who will go ahead and study further aspects of string theory, what I'm talking about is the analog of NS5. So there are D branes, and those are the guys that carry charge. They are solitonic objects. So okay, so what I want to say is that here we talk about a bosonic string, but we can do all the same in the case of a superstring. So you can ask, what will be the difference? Okay. So the difference, there will be not very many differences. So you will get exactly the same thing as here, except that you will have D going to be equal to 10. Okay, the critical dimension of the superstring is 10. You will have the same field, but then there will be a couple extra massless degrees of freedom. Okay, and so what we are doing, we are writing down an effective action for massless modes of the string theory. And so then you ask the same question, what is a possible solitons? And when you solve it, you will find out that there are D branes, and domain wall-like objects. So they will be charged. Okay, so I'm just going way too much. So the structure is very rich. And so one way to think about non-perturbative aspects of string theory is to think about the solitons of these low-energy effective actions that we just derived.
So these terms, connected terms, such as the inbreak of other orders alpha, right?
No, I didn't. Okay, so
as you said, we have the soliton. We just collect all the orders of alpha, right?
No, you don't need to. So you see the solitonic objects at this level in this approximation. So the solitons in string theory are not highly curved objects. That's why it's consistent to describe them in this effective action. By the way, do you guys know what I keep saying low energy effective action? What do I mean by that? You guys know what I mean by that? I mean, that's kind of another way, I would say, very physical way of thinking about what I just derived. You know? You just like the word, right? I never ask. Yes or no? So should I say a few words about what I mean? Okay, I'm going to say a few words. By the way, Clifford Johnson. So you might have a course. Cliff might teach a course about low energy effective actions. So you will learn lots about them. But let me. Okay, so I'm trying to come up with on the fly if I can write down. Okay, so suppose so I'm going to explain you how you can think about what we get here, and how you can think about this alpha prime expansion on the example of some simple quantum field theory. So we talk about Q of T as low energy. Okay, by the way, this is important, and you guys never asked me. Okay, what you didn't ask me? What's kind of unsettling about this effective action, right? So I wrote the effective action, and I talked about the condensates of massless fields. So what I was missing, what am I keep missing and kind of never talk about, and you guys are happy and never ask. What is string theory, right? So string theory has lots of degrees of freedom, right? So it has tachyon, it has massless degrees of freedom, and it has what? Infinitely many number of massive degrees of freedom. So what?
Energy. So it's for low energies, right?
Right, so it's low energies. And so where I am heading is that, what do I mean, right? So why am I not writing down the actions that involves massive string modes, right? That's a way to think about it. And so what I'm going to do, I'm going to explain you how you can think of this, okay? So you can think of this that if I would include all massive string modes and kind of write down the condition for the Weil invariance, it will be incredibly complicated worldsheet sigma model, right? But I would have to repeat all the same bands. Then I would get an exact action, right? I would get an exact space-time action that's coming from a string seed, including, infinitely many fields of arbitrary high spin and infinitely many derivatives, right? So in which sense do I do that? And that's what Alex was mentioning. So the way we have to think of this in the context of low energy effective action, low energy approximation. So let me give you an example. So suppose I have a Lagrangian del phi squared. So I'm doing it in 4 dimensions, right? So I'm just doing quantum field theory in 4 dimensions. And so instead of having infinitely many massive degrees of freedom, I'm going to look at the example when I have 2 fields, del phi squared, and then I have a potential, right? Potential and coupling, so of 2 fields. So I'm going to assume that my field phi is massive, but the field chi is massless. But on the other hand, there is a coupling plus g, say chi squared, phi squared. So there is this type of coupling. And so what will happen is that so if I look, so this guy is massless, but and I'm going to assume that my interaction between chi and phi field is positive. So the effective mass, so this guy, I can write down effective mass squared times phi squared. So this effective mass and effective squared is m squared plus g chi squared. And so it's always larger than m squared, right? So what is happening is that my field phi is always massive. And so here, what I have a quantum field series that involves 2 fields. One is very light field, chi. There is no mass charge, so it can easily fluctuate. But the other field is a massive field. And so the question you might ask, how do I get, so this is a Lagrangian involving chi and phi, and how do I get from this into Lagrangian involving only light field, chi? So that's the idea of constructing effective action, low energy effective action. You look at the massless fields and you write down the Lagrangian that describes the interactions between them. So the same idea is in the string theory. We have infinite power of massive fields. And what we are doing, we want to forget about these massive fields, and we want to talk only about light fields, massless fields. We don't talk about tachyons because in the case of a superstring, the tachyons are not there. And so what I'm going to do now, I'm going to show you in this particular example, how do we get rid of this massive field, and what is the effect of getting rid of this massive field? You will see that that kind of implies a high derivative correction, right? So all these alpha prime corrections here were high derivative corrections in the whatever fields are left over. Right? Good. So yes. Sorry. Wait. I'm just thinking of. I'm just gonna make it this way. So. Yes. Yes, that's. So what I want to do, I want to do exactly this. So I'm going to start with this effective field involving massive and massless field, and I'm going to say that if I'm looking at the scattering or any processes which cannot excite the massive field, which means that it always satisfies its equation of motion. So I'm going to integrate it out, and really integrate it out, replace by its classical equation of motion. So let me do that. So in other words, I'm assuming that the equation of motion for the field phi always satisfied. So I have here 2m squared phi plus g chi squared equals to 0. Right? So that tells me that phi equals minus g over 2m squared times chi squared. And so now, so this is a classical. So if my my low energy field phi, I continue thinking of it as a quantum field. And so what I'm saying that the massive field must sit at the vacuum expectation value that satisfies its classical equation of motion, which implies that I neglect the fluctuation in this massive field. So solving the equation of motion implies that I have this condition, and now I can go back and substitute. So I have the potential for V of phi and chi, and so now this becomes a low energy effective potential involving only chi. So this is just m squared and times phi squared, so g squared over 4m to the fourth chi to the fourth, and then I have plus, sorry, minus g g chi squared, and then I have g squared over 2m squared. So chi to the fourth. So what it is, it's minus g squared over m squared chi to the fourth, right? So in this effective Lagrangian, it will involve only the field chi here. I will have a chi kinetic term, and I will have a potential for the chi field. And so notice that what I did by integrating out a massive field, I'm generating a non-renormalizable interactions, right? 1 over m squared is the same as length squared, right? So I'm generating kind of alpha prime corrections. So that's why the way to think about this effective action for the massless modes of the string, and in particular the series of this alpha prime correction. So those guys will come up after I integrate out massive string modes. Okay. All right, guys. So are there any questions about this? And if not, then I am going back to Alex's question about compactification.
One question.
Yeah.
But here we have only one additional massive field, and string theory infinite number.
Right. So
how we can expect what they give us in if our energy is still low, but they can contribute to vacuum, right? So
right. So the answer to your question is there is an infinitely many fields, but there is always a finite number of fields up to a certain energy scale. So what I can do, I can integrate the fields. The first two fields.
Other fields can also contribute.
Yes, they will contribute at higher orders. So say the first level field will contribute to the alpha prime square. The second excited level contribute alpha prime cube and so on. Sometimes what happens is that there are cancellations. So for example, in the case of superstring, what happens in particular type 2B superstring, what will happen is that the first correction here come on the alpha prime cube. So there will be no alpha prime squared corrections. The next, it just isn't there. But then there are other strings here, the so-called heterotic strings here, in which there is alpha prime correction. So the structure you have to do a hard work, but it can be done. And there is a well-defined framework how you're going to do that. And the outcome of that hard work is that you have additional corrections to Einstein gravity, and they are specific to what kind of string you look, whether it's open string or closed string. And
okay, so if we rise our energy, we will get
high derivative, yeah.
Not high derivative, but zero order terms, right? Or no, if our energy is
well, it depends.
large.
Again, you have to. Okay, so here, let's look at this model. So in this model, I have only one massive field. So as long as my energy is below the mass of this field, I cannot excite it, which means that it is consistent to integrate it out and think of it as a classical field. But if I am above this, then I cannot integrate it out. Because if I am pumping up more energy in the system than the mass of my field, then this field can get excited, so it will start oscillating. And by doing this analysis, what I assumed that it doesn't oscillate. Okay. So, but now suppose I have a third field which has mass twice the mass of this guy. Then in between, so what I can have say another field, data, right, which has a mass 4m squared, data squared. So then there is a gap, right? So how's the spectrum? So there is a massless, so my field chi is here. Then there is m squared field. So this is my phi here. So m 0, and then there is 2m. That's where my zeta field is. So so it depends. Your effective action approximation depends what kind of processes you start. So if your energy is somewhere in here, then you can still integrate this, but you keep this. You have to think of this as at this energy scale. You think of this as a theory involving two quantum fields, two fluctuating degrees of freedom. And up here, if the energy is up here, you have three fluctuating degrees of freedom. If I am up here, then I have a single fluctuating degree of freedom. This field chi. And once you do this kind of integration out, that simply corresponds to the approximations, this alpha prime approximations that you're doing here. So in some sense, the string theory, the spectrum of string theory is equally spaced, right? At least in backgrounds which are close to Minkowski spacetime. All right, guys. So no time. So what we're going to do? So I will next week, I will talk a little bit about convectifications, and then we go ahead and look at the wild Hans diffeomorphism part in the measure of the follicle path integral, and we'll try to discuss some subtleties that will come up there, and slowly moving towards graviton scattering and the Veneziano amplitudes. All right, guys, see you next week.